Okay. Okay, so today we'll do some problems related to week number 8 of quantum mechanics and molecular spectroscopy. So is my screen visible? Hello? Okay. So the first question is, for the simple harmonic approximation in the vibrational spectra, which of the following is true? The force constant is the second derivative around the equilibrium point. The vibrational frequency is directly proportional to the force constant and inversely proportional to the reduced mass. For a fixed vibrational frequency, force constant is directly proportional to reduced mass. Force constant is greater for heavier isomers. Okay, let me do this then. Okay, we are approximating that this situation, this system is approximately equal to simple harmonic oscillators. So the potential will be like a parabola, right? So this is potential in terms of R, and this is R naught. Okay, so we know from the class that the force constant K will be del square V over del R square at R equal to R naught, right? So the force constant is the second derivative around the equilibrium point. This is correct. Second point is the vibrational frequency is directly proportional to the force constant and inversely proportional to the reduced mass. Okay, let's see. We know the force constant is m omega square, right? Where m is the mass of the particle and omega is the rotational or angular frequency. I can write omega as 2 pi nu, right? So in that case, for our system, m will be replaced by reduced mass, right? So k will be mu omega square. Okay, then in that case, omega will be k over mu root over, right? And this omega is nothing but 2 pi nu, which will be equal to root over of k over mu. Mu will be 1 over 2 pi k over mu. So we see the frequency is proportional to the reduced mass as 1 over root over of root over of mu, and it's proportional to root over of k. So in the question, the vibrational frequency is directly proportional to the force constant and inversely proportional to the reduced mass. It's not correct. It's proportional to the square root of force constant and inverse proportional to square root of mu. Okay, so second option is not correct. Okay, for the third point, for a fixed vibrational frequency, the force constant is directly proportional to the reduced mass. Okay, so for a fixed mu, k will be proportional to mu. Now we can see from this relation, for mu fixed, then k is equal to mu times omega square, right, or mu times 2 pi nu whole square. So k is directly proportional to mu. Okay, so in this case, for fixed vibrational frequency, force constant is directly proportional to reduced mass is correct. Okay, then the force constant is greater for heavier isomers. Okay, as we have seen, force constant is directly proportional to mu, and this mu for any molecule, let's say A and B, the reduced mass will be Ma times Mb divided by Ma plus Mb. Okay, so isomers means what? There will be let's say some diatomic molecules, HCl, atomic number of H is 1 and chlorine is, let's say, 35. Okay, isomer of this molecule can be deuterium with chlorine. You see, the atomic mass number is 2 here, so mass number is increased compared to this one. Let's say this is A. This is system A and this is system B. So for this case, mu will be 1 times 35 divided by 1 plus 36, right? So this will be 35 over 36. For this case, let me write it properly. This is 2. Okay, so for this case, mu will be 2 times 35 divided by 2 plus 30, which will be 70 divided by 37. So clearly this one is greater. For this molecule, the reduced mass is greater. So if reduced mass is greater, then force constant will be greater, right? So that HCl, this is for BCl. Okay, so mu of BCl is more than mu of HCl. This implies force constant of BCl is more than force constant of HCl, right? So for heavier isomer, so this is a heavier isomer of this A. Okay, where this For the case of A, there was hydrogen, and here in this case there was deuteron. Deuteron is nothing but one proton and one neutron, and so it's the isomer of this molecule. Okay, so the force constant is greater for heavier isomers is correct statement. Okay. Which of the following statement is true for heavy isomer molecules? Okay, bond length increases, the rotational constant decreases, bond length decreases, rotational constant increases. Okay, so in the previous question we saw heavy isomer means what? There will be, let's say there was some molecule HCl, isomer of this is DCl or H2Cl. Okay, so this is a heavier molecule than this one, right? So in this case, what will happen to their bond length? Okay, any guess? Okay, so if the isomer is heavy, then in that case the bond length will decrease, like, so this is HCl, so R naught is the bond length, and this is T, that means there will be two like one proton and one neutron will be there. So we know for this case the reduced mass will be more, and for compared to this case, right? So mu of HCl, mu of DCl will be more than mu of HCl, right? Now if we consider, let's assume their moment of inertia is constant. Let's say for HCl equal to DCl, then in that case what will happen? Mu R naught square for HCl will be equal to mu for DCl, right? Now we know DCl is more the reduced mass for DCl is more than uh, the reduced mass for HCl. Okay, so in that case, what will happen? R naught square for HCl. Let's write in terms of DCl. You want to check whether the reduced mass is increasing or decreasing. Okay, this will be mu of HCl R naught of HCl. Okay, so we know reduced mass of DCl is more than reduced mass of HCl. So in that case, this factor will be less than 1, right? Or it will be small. So let's say it is some 0 point some point, let's say 0.98 something, this ratio. Okay, so we see in this case the bond length for DCl is decreased by some factor compared to HCl, right? So in that case, bond length will decrease. Okay, now what about the rotational constant? So in the last question, we saw that K is directly proportional to mu. Right, K is directly proportional to mu. So in that case, we know mu of DCl is greater than mu of HCl. Right. So this will imply that K of DCl will be greater than K of HCl. Right. So DCl and HCl are isomers, and the heavier one will have higher force constant compared to the lighter molecule. Okay, so in this case, if then the rotational constant increases. Okay, okay. Sorry, this won't be rotational constant. This is force constant. We are considering bidirectional motion. Okay. So rotational constant is B, right? We are talking about K, so it's vibrational constant. not rotational constant. This is rotational constant. This is K is force constant. Okay. Okay, then moving on to the next question. Which of the following is true? Rotational constant is directly proportional to molecular reduced mass and inversely proportional to the bond length. Rotational constant is directly proportional to molecular reduced mass and inversely proportional to the bond length. And the rotational constant is inversely proportional to molecular reduced mass and inversely proportional to bond length. Or the rotational constant is inversely proportional to the molecular reduced mass and inversely proportional to the bond length. Okay, we know from rotational spectroscopy the rotational constant is denoted as B naught. Okay, this is as rotational constant. And we can write this rotational constant in terms of moment of inertia as h over 8 pi square, h square over 8 pi square c I, where this I is moment of inertia. Right. Now we know moment of inertia we can write as mu times r naught square, where this mu is what? Reduced mass, and r naught is the bond length. Right. Now substituting this in the above equation, what will we get? V naught will be a square over 8 pi square c mu r naught square. So what do we see? V naught is inversely proportional to inversely proportional to reduced mass and it's proportional to bond length as inverse square. This is bond length, right? This is rotational constant. So what we see? Bond length is inversely proportional to reduced mass and it is inversely proportional to the square of the bond length. So which option is this? Inversely proportional to reduced mass, inversely proportional to bond length. Okay, this is the correct answer. Okay. Moving on to the next question. According to Condon approximation, which condition is true? approximation we use to approximate the electric moment of nucleus, because the electric moment of nucleus is very small compared to the electric dipole moment. That's why what we do, we approximate the nuclear dipole moment to be very small. So the correct answer is B answer. Right. It is also contribute to the spectroscopy, but its contribution is very negligible compared to the electron contribution. So the correct answer is B. Okay. Okay, moving on to the next question. The selection rules for particle in a box are which are? These are the options. Okay, let me tell you what is delta n and what is capital N. So, for particle in a box, we can consider the initial state to be Ni. Let's say initial state is Ni and the final state is Nf. Right. Now we will define the transition moment integral, which will be the integration from 0 to L. Let's say this psi initial dipole moment psi final dx. Right. Now, if we consider this mu to be, let's say this is dipole moment, right? So it will be charge times the distance. Let's say charge is constant A and distance is x between the two particles. Okay, separated by some distance x. So we can write this as 2 root over 2 by L sine. Okay, this should be psi f mu psi a. Right. So in that case, this will be sine nf pi x over L times ax 2 over L sine ni pi x over L dx from 0 to L. Right. Now, if you solve this, like it's been solved in week number 8. So what you will get this value to be A over L. This is L over delta n pi whole square times minus 1 to the power delta n minus 1 minus L over capital N pi square minus 1 to the power capital N minus 1. So what is delta n? Delta n is nothing but NF minus Ni, and capital N is NF plus Ni. So from this transition moment integral, you can identify if delta n is odd, then what will happen? This will be negative, right? So So in that case, negative unit it will survive. Okay. So if delta n is negative, sorry, delta n is odd, then what will happen to capital N? Delta n is odd, that means NF is odd and NI is odd. Or no, delta n is odd means one is even, another one is odd. Okay, let's say NF is odd, NI is even, or NF is even, NI is odd. So in that case, the difference will be odd. So what will happen to the sum? Sum of one even and one odd number is odd, right? So if delta n is odd, then capital N will also be odd. What will happen in that case? This will be non-zero, right? This will also be non-zero. But let's say if it is even, that means both NF and NI are even, or both NF and NI are odd. In that case, what will happen? Delta N will be even, and capital N also be even. If both two numbers are even, then it will be even, and if both are odd, then their sum will also be even. So in that case, what will happen? This minus 1 to the power delta n, it will become 1. So 1 minus 1, it will go to 0. And similarly, here 1 minus 1, it will go to 0. So if delta n is even, this will automatically imply capital N will also be even. So in that case, what will happen? The transition moment integral will vanish. Right. Now, if delta n is odd, this will automatically imply capital N will also be odd. So in that case, this transition moment integral will be non-zero. Right. So what we want? We want the transition moment integral to be non-zero, so that the transition could occur. So this is known as selection rule, right? So the transition moment integral should be non-zero to make some transition. So if it is 0, then there won't be any transition, right? So the selection rule will give for the case where this transition moment integral will be non-zero. So this is the condition for that. Delta n should be odd and capital N should be odd. So C is the right answer. Okay. Can move to the next question. If minus d square over dx square is the curvature operator, then acting on wave function sin cx, then what is the eigenvalue of this operator? So this is a very simple quantum mechanics question. I think you should try. Let's take 1 minute and tell the answer. Okay, anyone? Okay, let's do this then. So what is the eigenvalue equation? You have an operator, let's say A, operating on some state, let's say psi. Okay. So when this function will be called as eigenfunction. So this function psi to be called as eigenfunction, it has to satisfy some condition. What is the condition? So any operator operating on this state, after this operation the state should not change. Okay. So this after this operation the state should not change. So this operation should be proportional to the state. And that means what? It will give some constant value, let's say lambda, and the state will remain psi. So this is the eigenvalue equation, right? So what is the meaning of this eigenvalue equation? Like if you imagine three-dimensional surface like Cartesian coordinate, let's say this is x, y, and z, and my operator is, let's say, is stretching. Stretching means what? If you have a stretched rubber band, same kind of proposition. Let's say you have a rubber band and you are stretching it, and let's say this operator is acting along x-axis. That means the stretching is along x-axis. So in that case, what will happen? This x-axis, it will be stretched to some different position, or let's say there is some point A marked here. So after this stretching operation, it will shift to this position. So what happened after this operation? The position changed, right, of this A position is changed, but the direction is same. So in this analogy, we can say this ik is the eigenstate, and the stretching, let's say this A prime is 1.5 times A. So this 1.5, that means the amount of stretch is the eigenvalue. Right. So this is an analogy. So you can apply this eigenvalue equation. So what is the operator? Here operator is A is minus d square over dx square, and the state psi is sine 3. Now if I operate A on psi, what I will get? Minus d square or dx square over sine 3x. So let me do one derivative at a time. So it's d over dx. So after first derivative, what will happen? Derivative of sine of 3x is what? Anyone? Hello. Can you hear me?
Yes, sir.
Okay, so it's a simple question. You read it. So there is a operator minus d square over dx square, and the wave function is sine 3x. So what is the eigenvalue? This is the eigenvalue equation, right? So here psi is sine 3x and the operator is minus d square over dx square. So you have to operate on this state sine 3x. So let's operate one derivative at a time. So what will happen if I do one derivative of sine? So it will be cos x, right? And the constant will come out using chain rule. So this is cos 3x. Now if I apply the derivative once more, so derivative of cos is minus sine. So this will give me minus 3 times 3 sine. Okay, there was one minus already, so this will be plus sine 3x, right? So this will be 9 sine 3x. So our equation is minus d square over dx square sine 3x equal to 9 sine 3x. Then what is the value of what is the eigenvalue in this case?
9.
Yeah, correct. Okay, then moving on to the next question. To a good approximation, the microwave spectrum for HCl consists of series of equally spaced lines separated by 6.2 into 10 to the power 11 Hz. Then calculate the bond length of HCl. So any idea how to proceed through this equation, this question? So what is given? The line separation is given. So we know all the lines are equispaced and the separation length is 2b, right? So what is given? 2b is given. Okay, so what we have to calculate? Bond length r naught you have to calculate. So this b means you have to calculate this b is what? This is rotational constant, right? Now do you know any relation between b and a moment of inertia?
B is equals to h by 8 pi square C I E.
8 pi square c, no, it's already in Hz, so we don't have to multiply c, it will be only this one. And what is this I? This is moment of inertia. What will the form of moment of inertia?
Mu r square.
Mu r square. So we have a relation between b and r naught, right? Just let me substitute this. So this will be h over 8 pi square mu r naught square. Okay, so what is given? The separation is given, that means 2b is given, right? 2b is given, you have to calculate r naught. So can you do this?
Yes.
Okay, then let's take one or 2 minutes and tell me the answer. So what is the value of h? This is 6.626 times 10 to the power minus 34 joule second. Mu have to calculate. Molecule is given HCl. So mu will be 1 times 35 by 1 plus 35. So this is 35 divided by 36. So it is in terms of atomic mass unit. You have to convert it into kgs. So you have to multiply some value like 1.67 times 10 to the power minus 27. So if you multiply this factor, it will be converted to kg unit. Okay, so mu you got, h you know, so r naught square will be h over 85 square mu b. Okay, so we have 2b here. Okay, let me write down this. R naught will be root over of h over 85 square mu b, and we have 2b equal to 6.26 times 10 to the power 11 hertz. Okay, now I have h value 6.626 times 10 to the power minus 34 divided by, let's write it 4 pi square. Mu is 35.
R is around 1.66 angstroms.
1.66.
Angstroms.
I'm getting 1.29. Probably some factors will be here and there. That's okay, but order is correct. Okay, so let me finish writing this. This will be 10 to the power minus 27, and 2b I have. So I can write 2b times 4 pi square, right? And root over of all this. Okay, 2b value we have, and all the parameters are we already got. So if you do this, you will get 1.29 Armstrong. Okay, just verify. Maybe some calculation mistake. Maybe I have also done. Check it. Okay, good. But the order is same, Armstrong. Okay. Okay, then moving on to the next question. The energy separation for this carbon and oxygen molecule for rotational energy between j prime equal to 3 to j double prime equal to 9 is 24 centimeter inverse. The rotational constant for this molecule will be what? So any idea how to proceed?
You can use mu bar is equals to 2b into j plus 1 formula. Delta E we can calculate
What mu bar?
is equals to 2b into j plus 1.
Okay. Yeah. Right.
Delta E you can calculate from here.
Yeah. Right. Mu bar is what? The line separation, right? But this formula is valid for what? Adjacent lines, right? Okay, if it is j and this is j plus 1, then the line separation will be given by this. But see this case, it's 3 and here it's 9. So will this formula work? Of course it will work, but we have to simplify the question first. So this formula is for what? For adjacent lines, right? J and j plus 1. So we have the transition from 3 to 9. So what we can do, and we know for rotational spectroscopy the line separation between adjacent energy levels will be always 2b. Now what we can do, we can calculate how many adjacent lines are there, or how many lines could be possible between 3 to 9. Let's say our starting state is 3, then it can go to 4. So in that case this formula will be applicable, right? So in this case the separation will be 2b, right? Now I can go 4 to 5 for this case also, the separation will be 2b, right? So similarly 5 to 6, 6 to 7, 7 to 8, and 8 to 9. So how many lines are there then? 1, 2, 3, 4, 5, 6. So 6 lines are there. So 6 times 2b, right? Like there are 7 states and 6 lines, right? So this is 3 and 3 more. Okay. there are 6 lines, so total length will be 6 times 2b, right? So this value is given. (24 centimeters). So this 6 times 2b is 12b. It's given as 24 centimeter inverse, right? So from this we can get b. Then we can calculate the rotational constant for, okay, there are two kinds of molecules. There are isomers, like here 12C 16O, here 13C 16O. So from this, let's say we can calculate B. This will be 24 over 12. This will give us 2 centimeter in. So B we got. Now in terms of B, we can write one formula like h over 8 pi square c times I. This is the relation between moment of inertia and rotational constant, right? So this is for 12C16O. Okay, you see, this is for 12C16O. Now for the case of 13C16O, what will change? There is extra one nucleon, right? So for that case, what will change? Mu can change, right? The radius, it's very small, so its change is also very small. So let's assume the radius is almost constant. So in that case, what is remaining? The reduced mass, right? For this case, reduced mass will be 12 times 16 by 12 plus 16. Okay, let's say this is mu1 and this is mu2. So this will be 13 times 16 by 13 plus 16. So mu will be different for the two cases. Okay, and the bond length, it's already very small for molecules. So in this case also the change will be very small. So we are assuming it's almost same. Okay, this is looking like a square. Let me rewrite this as mu double prime. Okay, so what will change? The reduced mass will change. Where is this reduced mass is coming? In this moment of inertia, right? This is mu times r naught square. So B for 12C 16O we know. Now we have to calculate rotational constant for 13C 16O. That means we have to calculate B 13C 16O. So everything we have, this value we have to calculate this. So do you know how to proceed from this? Any idea? What we are considering, every other value is same for those two systems, only the reduced mass is changing, right? So what we can do here, let's say this is h over 8 pi square c mu prime, let's say r naught square. So the same factor will come here also, right? Except this mu, this will be replaced by mu double prime. 8 pi square c mu double prime r naught square. Okay, if I take the ratio between these two, let's say B of 13C C16O divided by B of 12C16O. This will give me, so you see in these two equations everything is same except this mu prime and mu double prime. So the ratio will give us 13 is in the numerator, so it will give us mu prime over mu double prime, right? And this value we already got here is 2 centimeter inverse. So now I can write B13 C16O in terms of this B12 C16O times mu prime mu double prime, right? So what I did, we were given the spectral line for the transition from 3 to 9 to be 24 centimeter inverse. So from that we can get the value of B. Like the transition from 3 to 9 will contain 6 lines actually with equal spacing 2B. That means we'll have 6 times 2B to be 24 centimeter inverse. So from this we can get B, right? So this was for this molecule 12C16O. Okay, so we got the rotational constant for this molecule. Now we know for these two molecules, as these are molecules, the separation is already very small. So the change due to this isomorphism in the radius will be very negligible. So we are neglecting the change in radius. So we are considering R0 is same for both molecules. So in that case, what will happen? The reduced mass is the only thing which will be different for these two molecules, right? So the reduced mass will change. So we know the rotational constant in terms of reduced mass by this relation. So for these two molecules we have this relation. Now if I are taking the ratio, we are getting in terms of reduced mass ratio. So what we have to calculate? We have to calculate the rotational constant for this molecule 13C16O. So we already have this one and we calculated these two parameters. Okay, if I substitute all these values, what will have? 2 times mu prime is 12 times 16 divided by 12 plus 16. Now it is 28. 12 times 16 by 28 divided by 13 times 16 divided by 29, right? Now if I solve this, what I will have? 16 will cancel and I will have 2 times 12 times 29 divided by 13 times 28. So if you solve this, it will be nearly equal to 1.9 centimeter inverse. Okay, so let's check if we have this option. Yeah, it will be close to this one. Did you get this? Hello? Did you get this solution, or do you have any doubts? Okay, I guess you don't have any doubt. It's pretty straightforward. We calculated B from, like, the separation was given, so from that we calculated B, and B in terms of reduced mass relation we know already, and we have to calculate the rotational constant of this isomer. Then if we take the ratio, we are getting in terms of reduced mass, and after putting all the values we are getting this value. Okay. Okay, moving on to the next question. The correct statement from the following set, which will be the correct statement? So are you there? Okay, so let me read this. If Q is the displacement from equilibrium from a harmonic motion, the potential energy is proportional to Q. Is it correct? If the motion is harmonic motion, what is the form of potential? Potential will be half k x square, right? This is harmonic potential. Here the displacement is given to be q, so this x will be replaced by q. So what we see, the potential is proportional to the square of the displacement. So it's not directly proportional to q, it's proportional to the q square. So this is not correct. Okay, what about the second option? If the vibrational frequency nu bar for HCl is this much, its 0 point energy will be this much. So this is a harmonic potential, so the energy will be V plus half plus this wave. Okay, and this is the quantum number for this vibrational motion. And we are told this energy is 0 point energy, that means B will be 0. So in that case the energy will be nu bar over T. Right, so nu bar is given to be 2990 divided by T. So the 0 point energy will be 1495 centimeter inverse. So this is correct. Okay. Okay, then the next option, the correct order of vibrational frequency of OH, O2H, O3H, where this x1, x2, x3 are frequencies. Okay, so what is the relation between these frequencies? So if the motion is simple harmonic motion, then we know the force constant will be equal to m omega square, right, from simple harmonic motion. So in spectroscopy, what happens? This m replaces by mu, and this omega we can write as 2 pi nu, right. So from this, what will have? Mu times 2 pi nu square. This is equal to force constant. Okay. Now what we can do? We can write in terms of this frequency. This 2 pi mu will be equal to k over mu root over, right, or nu will be 1 over 2 pi k over mu, right. Now what we observe? We observe this frequency is proportional to 1 over root over of mu. Okay. Here this frequency is given as x, so this is, let's say, x. Okay. Why we wrote this in terms of mu? Like there is force constant also, but you see there are isomers are given. That means only some nucleon number is changing for these molecules. So in that case, what will happen? Which quantity will change dominantly? The reduced mass. This is Ma times Mb plus Mb. So for isomers, the dominating change will be coming from the reduced mass. That's why we wrote the frequency in terms of the relation of frequency in terms of reduced mass. So this frequency is given in as x in the question. So so the frequency x increases as mu decreases, right, or x decreases as mu increases. Okay, so we have 3 isomers. OH1, O2H, O3H. So what will the relation between the reduced mass between these two? So we know the reduced mass formula here. So for this one, it will be 1 times 16 divided by 17, right. So for this one, this will be 2 times 16 divided by 2 plus 16, that means 18. For this one, this will be 3 times 16 by 3 plus 16, that means 19. So what do we see? Mu is increasing for these 3 isomers as the number of nucleons increasing. Okay, so let's write this as prime, this is double prime, this is triple prime. So what will happen to the frequency? Then we saw the frequency is inversely proportional to the square root of reduced mass. So as reduced mass is increasing, frequency will decrease, right. So this is x1, x2, x3. What will happen? this will be more for smaller reduced mass, and this will be less for high reduced mass. So this will be the relation, right? Are you getting? Okay, let's check. Yeah, we have this relation. For these isomers, the frequency will the relation of the frequencies will be this. So C is correct. Okay, then moving on to the next option. The fundamental vibrational frequency of diatomic molecule appears at 1880 centimeter inverse. Its first overtone will be at 940 centimeter inverse, and assuming anharmonicity is anharmonicity constant is 0. That means we can assume this purely harmonic oscillator. Okay. So as we are considering it to be purely harmonic, then what will be the fundamental vibrational transition? It will be from V equal to 0 to V equal to 1, right? This will be fundamental vibrational transition. Right, from ground state it will go to first excited state. What is called then first overtone? So if the transition is happening from ground state to directly to the second excited state, then this transition will be called first overtone. Right, now we have considered the enharmonicity is 0, that means it's purely harmonic. So in this case, what will be the energy? Energy will be V plus half times the wave number, or omega, whatever you can say. This is given in terms of centimeter inverse, so you can say this will be, let's say, wave number. Okay, so what is being asked? The first overtone will be 940 centimeter inverse, and the fundamental line is given 1880 centimeter inverse. Okay, let's check then. Okay, then the change of energy will be this first overtone, it's this state minus this state, right? We need to calculate the transition from 0 to second state. So the change in energy for this case will be 2 plus half omega bar minus this 0 plus half omega bar, and omega bar is given 1880 centimeter inverse. So if you solve this, what will get? 2 omega bar, or omega bar is given, so in this case it will be 3760 centimeter inverse. So the first overtone will be 3760 centimeter inverse, but it's given to be 940 centimeter inverse, so this is wrong. Okay, any doubts? Okay, I guess no. Then we will move to the next question. The different type of energies associated with molecules are, so these are the options. What is the answer? Hello? Okay. The different type of energy associated with a molecule. Okay, it can be electronic energy. That means there can be some transition between the energy levels for this molecule. Like if one atom is considered, then some transition between the energy levels can be happen. So electronic energy will be there, and if it is vibration, like molecule, it can vibrate along its axis, so vibrational energy will also be there. And if we consider this molecule to be a rigid um, rotor, then it will have rotational energy also. So all kind of motion and all kind of energy is allowed for a molecule. So the right answer will be D. Okay. Okay, then moving on to the next question. The region of electromagnetic spectrum for nuclear magnetic resonance is which one? Okay, the correct answer will be D, because the frequency needed for nuclear magnetic resonance matches with the radio frequency. The frequency is very low. That's why radio frequency is required for nuclear magnetic resonance. Okay, then moving on to the next question. At room temperature, which molecule has the maximum rotational entropy? So you might have studied from thermodynamics. What is entropy? The entropy can be stated in one way as the number of ways the molecule can be distributed among all the possible energy states, right? So if I state there are two states, one is excited state and one is ground state. This is excited state, this is ground state. Now this is a molecule, right? So it does not have to, as a whole, it will behave like a Maxwell-Boltzmann particle or classical particle. So it does not have to be following Fermi-Dirac statistics. So we can use Boltzmann statistics. So in that case, we can use Boltzmann distribution. Boltzmann distribution law. So it states the number of particles in excited state will be equal to number of particles in ground state times e to the power minus the energy of separation divided by kT, where k is Boltzmann constant. And T is the temperature, and epsilon is energy separated between this ground state and excited state. Okay, epsilon is this epsilon excited minus epsilon ground. Okay, so you see from the relation here, if epsilon is very large, what will happen? This factor will be very small. Okay, let me rewrite this: n excited by n ground is equal to e to the power minus epsilon by kT. So it's already given at room temperature, that means T is constant, so only variable is epsilon. So if epsilon is very large, that means what? The gap is very high between ground state and excited state. So in that case, what will happen? This quantity will be very small. So if it is very small, in that case, there this ratio will be very small. That means the distortion will be very small. It will have less entropy. Okay, we can write epsilon of excited state as this B times HC. Okay, so if B is large, that means what? The separation is very large, right? Like we know the separation between two states is 2V for rotational spectrum. Okay, so this B defines the energy separation. So if B is large, then this epsilon excited will be large. Then if this epsilon excited is large, then the separation will be very large. Okay, so if separation is very large, then this quantity will be very small. If it is small, then the entropy will be also very small. Okay, now we have 4 kind of molecules. Okay, so we saw the ratio is dependent on the energy difference, and this energy difference is dependent on the energy of excited state, and this excited state energy is dependent on the constant B. Okay, so we know like we have 4 kind of molecules, right? So what information do we know about these 4 kind of molecules? We will know its moment of inertia, or we will know its reduced mass and its bond length. We will know these parameters. right? So as the molecules, as these are molecules, the bond length difference between these molecules will be very small. Like if it is, let's say the bond length for hydrogen atom is some Armstrong, so for oxygen molecule it's also be some Armstrong, right? The same order, but the mass, reduced mass will be dominating quantity which will be changing, right? So what is the form for reduced mass? This will mass of m1 times mass of m2 divided by m1 plus m2. So among all these uh, four examples, which is the heaviest one? Oxygen. Okay, this is the heaviest one. The second heaviest will be nitrogen, then third heaviest will be deuterium, and the fourth heaviest will be hydrogen, right? So if I calculate their reduced mass, then what I will get? Mu of hydrogen is less than mu of deuterium, less than mu of nitrogen, it will be less than mu of oxygen, right? Now our excited state energy dependent on B. So energy is dependent on B, and B we know we can write in terms of this in terms of moment of inertia is h over 8 pi square I, or this I can write 8 h over 8 pi square mu r naught square. So we saw B is inversely proportional to mu. So in that case what will happen? B of hydrogen, B of deuterium, what will be the relation between these rotational constant? It will be reversed, right? So the rotational constant for hydrogen will be higher compared to the other molecules, right? So if B is higher, then E will be higher, yeah, okay. So if B is higher, then E will be higher, that means this energy separation will be higher, so entropy will be less. So entropy will be smallest for hydrogen, then it will come to deuterium, then nitrogen, and then oxygen. So the highest entropy will be possessed by oxygen molecule, right? Okay, I think it's clear, or do you have any doubt? Okay, then we'll move on to the next question. Okay, for a diatomic molecule AB, the energy for rotational transition from J equal to 0 to J equal to 1 state is 3.9 centimeter inverse. Then the energy for rotational transition from J equal to 3 to J equal to 4 state would be, okay, which one? Okay, there is a molecule AB, and the rotational transition from J equal to 0 to J equal to 1 is given to be 3.9 centimeter inverse. Okay, so the energy separation is, or in terms of wave number, this energy is 3.9 centimeter inverse. Let me write it as E bar, delta E bar. Okay, now delta E we know for rotational spectroscopy we can write as 2b times J plus 1. Or you know, and for rotational spectroscopy energy will be B times J into J plus 1, right? So if there is transition between 0 and 1, then in that case what will happen, the delta E will be B times J plus 1 into J plus 2 minus B times J into J plus 1, right? So if these are in terms of wave number, I am writing it to be bar. So if we take the difference, what we will get, delta E bar will be 2b J plus 1, right? And what is given, this delta E bar is given from 0 to 1 state. So this is 3.9. So from this what we can get, B. So B we can write delta E bar over 2b J plus 1, right? And we know as the transition is happening from 0 to 1, J value will be 0. This is delta E bar over 2b of, sorry, there won't be B, this is 2 times J plus 1, this is 2 times 1, so this will give us delta E bar over 2. Delta E bar is given 3.9, so B will be 3.9 over 2. So let me write it as B bar. Okay, so this B bar is 3.9 divided by 2, that means 1.95 centimeter inverse. Okay, so B bar we got. Now what we have to do, we have to calculate the transition line from J equal to 3 to 4. Okay, now for any adjacent transition we have delta E equal to 2b times J plus 1. This J is the lowest value. This is in terms of frequency. In terms of wave number we can write delta E bar is equal to 2b bar J plus 1, right? B bar value we already got. Now the transition is between J equal to 3 to J equal to 4. Yeah, so the J value will be 3 for our equation. So in that case, what will be the energy line? This will be 2b bar J plus 1, or 2 times 1.95 times 3 plus 1. So this will give us 8 times 1.95, or 15.6 centimeter inverse. Okay, so if there is a transition between J equal to 3 to 4, the transition line will be 15.6 centimeter inverse. Okay. Okay, moving on to the next question. So that the components of the moment of inertia of trigonal planar molecule aligned along y-axis are, okay, along x-axis and y-axis it will be 3m by 2, and along z-axis it will be 3 if all the masses are m units, and all the bond lengths are unit length, and all the bond angles are 120 degrees. Okay, so we are given a trigonal planar molecule. So I didn't draw it, but let me draw it here. So the molecule is like this. It's a trigonal planar molecule. So it is aligned, one of the molecule is aligned along y-axis. So we can take this axis as x-axis and this axis to be z-axis, and the bond angle is 120 degree. Okay, and every mass is m. Okay, now we need to calculate the moment of inertia along x, y and z direction. Okay, so you know, if there is a mass, let's say, and the rotation axis is this one, then the moment of inertia along this axis of this some mass separated by some distance r will be mass times distance square. Right, now for this molecule, if I consider the moment of inertia along x-axis, that means what? My reference axis is x-axis, and I need to calculate the distance along the x-axis of the masses. Okay, so what I can do, I can do one thing, I can project these masses along to x-axis. Right, let me redraw this. So as the angle is 120 degree, so this angle will be 90 degree, and this angle will be 30 degree. Similarly this one also. So if I project all the masses along the x-axis, what I will have, the contribution from this and this I will have along x-axis. The projection of this mass will be 0. Right, so the moment of inertia along x-axis, this will be sum of all the masses times the distance, let's say xi Okay, now how many contributions I am getting? I am getting contribution from this and this, like projection, that means distance contribution I am getting. The projection of this mass is 0, so its contribution will be 0 along x-axis. Okay, now the projection is this much, right? So this mass is m, this is also m, so this will be equal to, 1 second, okay, so mm, sorry, we are considering this axis, right? So we need to calculate the distance from this axis. So this already it is given unit distance, this is unit distance, this is unit distance. So contribution of this will also come, and its contribution will come partially as a projection. So I can write this m times 1 square, and from these two it will come as 2 times m times sine 30° square. As the distance is 1, so it's 1 square. This will give us m plus 2m. So sine 30 is, what is the value of sine 30°? This is half. Okay, this is square, right? So this will give us m plus m over 2, or this will be 3m over 2, right? Now if I calculate along y-axis, what will happen? I need to consider this axis. Okay, maybe if question is wrong, this should be z-axis and this will be y-axis. So in that case, I y will be sum over mxi square. So this will give me m1 square plus 2m, this projection, right? So this will be cos 30°, cos 30 square. So what is the value of cos 30? So root 3 by 2. This will give me 3 over 4. Okay, my mistake. This is y-axis, this is z-axis. So the projection, okay, along this one, okay, for x case, we needed to calculate this distance, like from the axis we need to calculate the separation, right? So this will give us sine theta, right? If the reference axis is this one, we need to calculate the radius with reference to the axis. So this is the distance for the first case. So this is sine theta. Okay, sorry for the mistake. So first one is correct. Okay, now for the second case, this is y-axis. So we need to calculate the distance of this molecule from this y-axis. So what is the distance? So this projection will give us the distance, right? This is cos theta. So it will come from these two masses, and the third mass, which is already in that same axis, the radius will be 0. So it will give us the same x. So this will be 3m over 2. Okay, now quickly do the z-axis thing. So I z, if you see, so if it is z-axis, all are in a plane. Let me draw this z-axis properly. So these are all in a plane. Okay, and every mass is at same distance from this z-axis, 1. Okay, so for this case it will be sum of mi xi square, it will be 3 times m 1 square, so this will be 3. Okay, so it will be this, yeah, we proved this. This will be 3m over 2 and L of z-axis, this will be 3. Okay, so it's time for today. We'll meet in the next class.